Welcome to the Supply Chain Analytics course. This is the third part of Lecture 13 on distribution logistics and the vehicle routing problem. Now let's try to focus more on how we can solve the traveling salesman problem. Here the problem is in which order to visit a number of customers so as to minimize the cost. And where this cost comes from, it comes from traveling from one node into another node in the graph. This is a very typical problem that it can be found in many other problems, and it is the simplest VRP case in which we have a VRP with only one vehicle. What are the available approaches for solving the TSP problem? Basically, we have two main classes of methods, heuristics and exact approaches. In the family of heuristics, mainly we have two kinds of methods. Construction heuristic approaches, where the goal is to find a feasible solution for the problem, a feasible tour or route for the TSP. And also improvement heuristics, in the sense that given a feasible solution, make some small changes in an iterative fashion and try to improve the feasible route that you have. What are the advantages and disadvantages of heuristic approaches? They are very fast. We can find a feasible solution very quickly, but we don't have an optimality guarantee. The solution that we will find, it is not necessarily the optimal solution for the problem. The performance of the overall approach depends on the problem that we solve. And also, the worst case performance, in some cases, maybe it is very poor. On the other hand, with exact algorithms, and in particular with integer programming approaches, and with the very well known, the branch and bound method, we can solve the TSP to optimality, and we can have a guarantee that the solution that we have is the optimal solution. But these approaches are typically very, very slow. And with the term slow, I mean that they consume a lot of computational time. Another disadvantage of exact algorithms is that they are difficult to include complications, and also sometimes it is difficult to include additional operational realities and constraints. If you are wondering what is the maximum size that we can solve with exact approaches, in the recent literature we have seen some problems with something less than 25,000 cities to be solved, and this is an example from the TSP from Sweden. What is the optimal visiting sequence to visit all towns and villages in Sweden? And if you look on the right at the figure, you will see the solution and the exact sequence in which the salesman visit the cities in Sweden. Let's initially focus on the simple TSP problem with one vehicle, no capacities, just minimization of the distance, no time windows, no compatibility restrictions, no restrictions regarding the driving hours and other driving regulations. Let's also assume that the cost matrix from traveling from one point I to another point J is symmetric. Symmetric means that the direction does not affect the cost. We will see three TSP construction heuristic. The first one is the so-called nearest neighbor, and the main idea is to add the nearest customer at the end of the route. The second will be the nearest insertion. Here, initially, we go to the nearest customer and we return to the initial point, and afterwards we insert the customers that they are closest to the route in the best sequence. Finally, with the savings method, we add the customer that saves the most to the route. Starting from the nearest neighbor method, the idea is to add the nearest customer to the end of the route. And you can see here, this is the nearest customer to the depot. this one here, and then this one here, and then this customer here. And if we move on, you will see that the next closest customer is this one, and finally we add this one and we return to the depot. On the other hand, the nearest insertion heuristic, as I said here, the idea is to insert the customer that is closest to the route in the best sequence. So we start with the closest customer to the depot, and we insert the closest customer into the route. So this one here is the closest customer to this link, and you can see at the second step where we have included this customer into the route. Next, the closest customer is this one, and we can insert this customer into this part of the route, and we do that. And next, the closest customer to insert into the route is this one here, and we do that. Next, the closest customer is this one here, and we include this customer here. You can see this happening here. And finally, we have this customer to be inserted into this link here. And you can see here the final solution. Now, regarding the savings method, here we have mainly 4 steps. At the first step, we select any city as the depot, and we call it city 0. We start with separate one-stop routes from the depot to its customer. The second step is to calculate all possible savings for joining 2 customers and eliminating a trip back to the depot, and this will be the formula that we will use for that. The third step is to order the savings from the largest to the smallest, and finally we form the final route by linking customers according to the savings that we have calculated at the third step here. Let's say that we have 5 customers, and we will denote this one as the initial starting point for the tour. And this table here shows the distances, or similarly the costs, between any pair of customers. Now, the first step is to begin by sending by forming one route with every customer that we have. So conceptually, we form routes from the depot to each customer like that, as shown here in this figure. At each iteration of the method, we will merge 2 routes, and with the term merge, we mean that we will remove this link, and we will add this link here if we want to merge these 2 routes here. And this is what we get. Next, we enumerate all other possible combinations. In particular, we calculate the savings for 1 and 3. And then we move on with the calculation of the savings for merging customers 1 and 4, for merging customers 2 and 3, for merging customers 2 and 4, for merging customers 3 and 4. Having calculated all savings, the next step is to order the savings that we have from the largest to the smallest. And this is what we get if we do that. And we start from the biggest one, and we start merging the routes. So the first one is to merge customers 2 and 3. So to do this merging here, and if we do that, we end up with this. Next is to merge route 3 and 4, to merge these 2. So to remove this arc, to remove this arc, and to create this one. And if we do that, we get this is the new route. And finally, we have to join 1 and 2 you can see this merging here, and if we do that, basically we see that there are no any other merging combinations left, because all customers, they assert at a single root, and this is the endpoint for the savings method. Now, regarding root improvement heuristics, here the basic idea is to start from a feasible root and then iteratively to start making changes in order to improve the root. We have, for this purpose, we have a lot of edge exchange heuristics. For example, switch the position of two customers in the root, switch two arcs in the root, or switch three arcs in a root. I will give you some examples later on about those. And we also have meta-heuristic strategies that they control the process of iteratively changing positions of the customer into the root. We have simulated annealing method, we have the taboo sets method, we have genetic algorithms, we have a lot of different variations here, and we will discuss these methods later on. Let me give you an example of a k-opt exchange method. Here the idea is to replace k arcs in a given TSP tour by k new arc, so as the result is still a TSP root. So if this is the original TSP tour, I select to replace this arc and this arc here with this one and this one, okay, and this is a 2-opt exchange in this case. A 3-opt exchange is similarly to exchange 3 arcs with another 3 arcs. So this can be an example of a 3-opt exchange move.